Okay, so I will get going. It's time. So it gives me great pleasure to welcome Abhay Ashtekar to deliver the 15th OSMU lecture of this year. Abhay is an Ivan Pugh Professor Emeritus of Physics and former director of the Institute for Gravitation and the Cosmos at Pennsylvania State University. Abhay did his undergraduate studies in India and then enrolled in the graduate program for gravitation at the University of Texas at Austin. He went on to complete his PhD at the University of Chicago under the supervision of Robert Garrosh in 1978. After Chicago, Abhay held several appointments at Oxford, Paris, Syracuse before settling at Penn State. An influential article written by Ashtekar and Garrosh in 1974 entitled Quantum Theory of Gravitation is testament to Abhay's involvement with quantum gravity from a very early stage. His transformative work came in 1986, this being the famous paper titled New Variables for Classical and Quantum Gravity. These new variables came to be known as Ashtekar variables and laid the foundation for the fields of loop quantum gravity and loop quantum cosmology. Few people have thought as deeply about quantum gravity as Abhay has. For nearly half a century, Abhay has been an inspirational and influential leader in this subject. Today, we'll hear from him on perspectives on the evolution and status of quantum gravity. Over to you, Abhay.
Okay, thank you. Can you hear me well?
Yeah, thank you. It's good.
Okay, all right. So as I said, that there is no discussion of either uh, octonions or standard model or unification of particle physics here. And I had sort of told this already to the organizers, and they said that as was just mentioned, that scope is actually of the series is enlarged. Okay, so I'm really going to talk about quantum gravity, and um, the organization is as follows. Um, I'm just trying to move the things if I can, so I can read my own slides. Just one second. The bar is, yeah, okay, good. Organization as follows. Um, First part, I'll just tell you about quantum gravity and evolution of the field or development of the ideas from my perspective. And then the second thing is going to talk about conceptual settings, and particularly I'll focus on string theory and loop quantum gravity, and then fundamentals of loop quantum gravity and theory versus observations, and summary and an afterthought. I was told that there's an extended discussion period, and in fact, TP Sinks did send me some questions from the organizers, so we can take them up in the extended period. And also, I couldn't fit in black hole, the status of black hole evaporation and such, and in the talk. And so, if there is interest, we can discuss this at all. I should say that my goal is really to convey the basic ideas and the current status. It's going to be a very broad overview, and I will summarize work of many, many researchers. And I apologize in advance that I will generally skip references because there are way too many and they will crowd the slides. A comprehensive treatise on various approaches to quantum gravity is in this Handbook of Quantum Gravity of Springer, which was published in 2025. And one part of it is on loop quantum gravity, another on string theory. There's also supergravity and other approaches. Um, so let me begin with the first simple part. Well, Einstein's resistance to accept quantum mechanics as a fundamental theory is well known. However, he had a deep respect for quantum mechanics and was the first to raise the problem of unifying general relativity with quantum theory. And this is not so well known. Already in his paper, which sort of came after his first paper on linearized gravity and gravitational waves in linearized gravity, he says, nevertheless, due to interatomic movement of electrons, atoms would have to radiate not only electromagnetic but also gravitational energy, if only in tiny amounts. As this is hardly true in nature because atoms are stable, it appears that quantum theory would have to modify not only the Maxwellian electrodynamics but also the new theory of gravitation, that is to say, general relativity. So almost a century has passed, more than a century has passed since Einstein wrote these words. So why is the problem still open? Well, usual answer is, of course, that there is no experimental data with direct ramifications on the quantum nature of gravity. And we'll return to this point in the discussion period. Uh, but recall that, I mean, this is not surprising because if you look at general relativity itself, the first taste of full nonlinear general relativity came in with gravitational waves in 2015. And that was 100 years after Einstein's discovery of relativity. And so technology just is that needed, it's just not with us. And so this is not surprising. But then, if this is the only point, then this should be a theory 7, because if there are no experimental constraints, then there should be a plethora of theory. I should be able to churn out a theory every day. But we don't have a single satisfactory theory. So this cannot be the whole story, that we do not have the experimental data is the main obstacle to having a quantum theory of gravity. And my view, the real reason is the following. In general relativity, gravity is encoded in space-time geometry, and the most spectacular predictions of the theory, which are to do with the Big Bang, the black holes, um, they and the gravitational waves, they emerge from this encoding of gravity into the very geometry of space and time. Um, and the problem really is that since if gravity is going to be quantum mechanical, then space-time geometry itself must become quantum mechanical. And then how do we do physics without a space-time continuum in the background? We need new concepts and new mathematical tools. We learn how to lift the anchor that tied us to a background space-time and sail open seas relatively recently. Now, there are several approaches and several voyages in progress to sail these open seas. Uh, and because there is no direct experimental checks, approaches are driven by intellectual prejudices about what the core issues are and what will take care of itself once the core issues are resolved. And here are illustrations of the different points of departure in this voyage. You begin with something as that you think is the most promising way of going where you want to go. And the first is really emphasis on mathematical structures. And these are all the approaches are really, I find that idea is very fascinating. So for mathematical structures, it is non-commutative geometry, as most of you know. The idea is that if I go to the, um, uh, the if you give me a regular manifold and if you give me a ring of function on that, then it is an abelian algebra. And then Gelfand theory tells us that if I know the spectrum of this abelian algebra, I can reconstruct the manifold. So somehow these algebras have already the information about this manifold. And so the idea is that, well, perhaps in what quantum gravity needs is not an abelian algebra, but really a non-commutative algebra, non-abelian algebra. And then we'll do some constructions which are analogous to what Gelfand taught us, and then that would give us this non-commutative geometry, and that could be the underlying idea. Then the second big idea has been causal sets, namely the fundamental things are not sort of, it is the causal relations between various points, this fundamental discreteness, and all we have is a causal structure between them, and then you write down some action from which the familiar physics is supposed to emerge. And then there is twistor theory, in which the fundamental space is not space-time, but twistor space, and space-time is going to be emerging out of the twistor space. Twistor space is inherently complex, and kind of already in the mid 1970s, Roger Penrose discovered this fantastic transform, the Penrose transform, which really relates differential solutions to differential equations in space-time to certain, these solutions can be obtained by certain integrals in the twistor space. And it's a very interesting non-trivial bridge between the two theories. But of course, so far, the considerations have been restricted to complex fields, particularly self-dual or anti-self-dual fields. Then the second set of approaches starts with quantum field theory as being fundamental, with this asymptotic safety program, which I think has made a lot of progress in connecting to kind of signatures of quantum gravity into particle physics, what constraints we have, what constraints we do not have, etc. Then there's a perturbative string theory, which was the starting point of string theory. And then that evolved into this ADF-CFT conjecture on the gauge gravity duality, which would say that, in fact, the non-perturbative string theory is a quantum field theory, but defined on the boundary. And the main task is to set up a dictionary between what is happening in the space-time and what is happening on the boundary. And then there is a third set of approaches which sort of really emphasizes what Einstein taught us, namely gravity is geometry. And this was the Euclidean quantum gravity approach pioneered in the Cambridge group by Gibbons and Hawking. And then there is, of course, Reggie calculus and loop quantum gravity and spin forms, on which, as requested by the organizers, I will spend the second half of my talk. So then the question is really, why is this variety of approaches? And because there is no direct experimental checks, approaches, as I said, are driven by intellectual prejudices about what the core issues are and what will take care of itself once the core issues are resolved. So I already said this, but this sounds strange at first. Isn't science meant to be objective? And these are all intellectual prejudices that we're talking about. And so it sounds weird at first. But I think the most succinct answer that I found and thoughtful answer is due to C.N. Yang, who just passed away. From his selected papers, he has written a commentary to his selected papers early on. And he says that test and style have so much to do with physics may sound strange at first, since physics is supposed to deal objectively with physical universe. But the physical universe has structure. And one's perception of this structure, one's partiality to some of its characteristics and aversion to others are precisely the elements that make up one's test. Thus, it is not surprising that test and style are so important in scientific research, at least when we begin some approaches like quantum gravity. Finally, of course, nature is what decides which of them are right and which of them are wrong. But in the development of the field, taste and style are really so important. So here are some illustrations of taste and style. And we saw just a while ago that there are a lot of approaches. And I just don't have time to spend, one or two transparencies on each. So I'm going to spend some time, just select the one on which a lot of work has been done over the last decades, and namely string theory and loop quantum gravity, and that is what I'm going to focus on in this case. So these are the two illustrations I will give about taste and style. So first is superstring theory, and it was developed mainly by high energy theorists. So at first, in this endeavor, unification of all interaction was a central goal. And in order to carry out this unification, it was thought one would need supersymmetry, higher dimensions, and that were at the foundation. And the hope early on was kind of the E8 cross E8 superstring theory would provide the unified theory of all interactions, and it would also be a unique theory that is perturbatively finite. Now it has been checked, but only to 2 or 3 loops. However, the perturbation theories does not converge, and it is not even Borel summable, as was pointed out by Gross and Perriwell. And now the view is that the known 5 perturbative string theories are limiting cases or corners of an unknown, yet to be known, not yet to be found, non-perturbative theory, which is called M theory, and M is typically stands for mystery, illustrating that we don't know what this theory is. Now, a major paradigm shift appeared in the 1990s, in the second half of 1990s, because of this bold conjecture due to Baldacena. And this is the so-called ADS-CFT or gauge gravity duality. And the idea here was that we would provide a non-perturbative definition of superstring theory in the bulk using a finite, well-defined gauge theory on the boundary. So the ingredients of this approach was, in order to specify this finite quantum gauge theory, one needed a conformal metric on the boundary. The idea was that space-time should be asymptotically anti-de Sitter. So anti-de Sitter, or asymptotically anti de Sitter, and it has a boundary. So, for example, if space-time is 4 dimensions, the boundary would be 3 dimensions, and one would get a conformal field theory, a conformal field theory on this boundary, and for that we need a conformal metric. And usual Penrose completion does give us a conformal metric, so that is good. But then the idea was that well, we should have supersymmetry, and 10 fundamentally we should have 10 space-time dimensions and a negative cosmological constant. And so many of these dimensions would be internal, and there will be some large space-time dimensions. The best known example is not with 4 large space-time dimensions, but with 5 bulk dimensions, large dimensions, and that compactified and some internal dimensions which are S5. But I think it is not often said or emphasized that in this best known example, the radius of these compactified dimensions goes like the cosmological radius, and this is very large internal dimensions. So if this were something like this were true in 4 dimensions, I have a six dimensional sphere here. If the radius is cosmological, then I should just be able to look up and see all these extra dimensions, and we don't see that. But nonetheless, these ideas drew a great deal of attention for good reasons, because they led to a lot of interesting guidelines and results in a number of fields which are unrelated to gravity, where non-perturbative results were established using techniques from gravity and supergravity. And the examples here are fluid dynamics, condensed matter physics, and QCD. And therefore, there's an answer, seems to be like it brought out some unforeseen unity in diversity. These are very diverse fields, and the same methods which came from string theory were applicable here, and also in mathematics, so in algebraic geometry, and so on. It made very interesting and remarkable contributions. So that is why I think it drew a lot of attention. But we can ask, well, what about gravity proper? I think that perhaps the most well-known success is the calculation of the statistical mechanical entropy of extremal black holes by Strominger and Wafa. But in the current understanding, these black holes, these extremal black holes, are actually unstable quantum mechanically, and this is something work of string theories themselves. And so the original calculation is now regarded as a fortunate coincidence. And there was a lot of discussion about this in this Stony Brook workshop, which just happened in the beginning of this month, November 2025, at the Stony Brook Simon Center, so people can look at it. And particularly the talk by Roberto Emperan is one sort of discusses these matters. So there is progress in counting. I mean, nonetheless, there is progress in counting these microstates of black holes using string theory techniques, but mainly almost all the work is done for near extremal black holes. And again, when I say near extremal, this near extremal is not in the astrophysical sense, it's really in the sense of string theory. So for example, in the Rice-Nosdam case, the difference between E and the mass, the electric charge in the mass, has to be of the order, very, very small, of the order of 10 to the minus, I forgot now, but maybe 60 or minus 120 or something, very, very small. And also it needs supersymmetric or BPS states of black holes, which are full supersymmetry for the argument to actually work, because one uses these non-renormalization theorems, which are protected by supersymmetry, so one needs supersymmetry. Now, for black hole evaporation, there are two main approaches that are being pursued by what was by former string theories. One of these approaches doesn't have much to do with string theory. The first approach, first of all, does. Idea here is that if in fact you have something like a gravitational collapse, then before the marginate trapped surface is formed, somehow there is a transition. And suddenly then, the usual description is not sufficient, and one has to go back to this 10-dimensional description provided by string theory with certain kinds of branes which are compactified in certain sense with some fluxes. And therefore, actually, that will give us some internal states, and those internal states are the same as those of the black hole. And then one wants to say that, well, so when there really never was a black hole, so there is no information loss paradox. There is this just first ball, which is like a ordinary star, if you like. It is radiating away, and one calculates the radiation, and one gets the Hawking kind of answer in the thing. And there is no kind of paradox here, if you like. There's nothing problematic, because there never was an event horizon or even a marginally trapped surface. The second approach is the so-called replica wormholes, which is more traditional. In the first ball approach, one is only talking about very restricted class of black holes and so on, and like the extremal black holes or near extremal black holes with certain supersymmetry and so on. In replica wormholes, one is much more general. One can talk about four-dimensional black holes that we sort of see, but it's a Euclidean approach, and one is only doing saddle point semi-classical approximation. Um, and so while there is progress, neither approach is complete, and both are significant limitations. And in this Stony Brook workshop, for example, each community had offered criticisms about the other approach. In both these approaches, somehow something unexpected has to happen at large macroscopic scales. In the first ball approach, for example, it is uh, when a star is almost formed the marginally trapped surface, but not quite marginally trapped surface, suddenly there is this transition. So it's really in a completely semi-classical regime. It could be, for example, supermassive black collapse to formation of a supermassive black hole, in which case the curvature is less than that in your room right now, and even then this transition is supposed to occur. And similarly in replica wormholes, certain certain effects are supposed to occur, which are kind of not semi-classically expected. So the current status of superstring theory is the following. Supersymmetry has not been found yet. Unification has not been achieved. Space-time does not have macroscopic compactified dimensions, and also no evidence for microscopic ones. So the macroscopic uncompactified dimensions were required, for example, in this uh, the best known model, in which we got ADS 5 times S 5. That is not found, but also there's no evidence for microscopic ones. And whereas supersymmetry requires negative cosmological constant, to the extent where cosmological constant it is positive, and the theory is not unique, there's a freedom of compactification leads to a swampland with some 10 to the 500 vacua. A broad summary of the status can be given as follows. This is from an article from the Institute of Advanced Study Princeton website. It was written by a science writer, Casey Cole, who was a reporter in residence there. The Strange Second Life of String Theory. It says, string theory has so far failed to live up to the promise as a way to unite gravity and quantum mechanics. At the same time, it has blossomed into one of the most successful tools in science. So now let me turn to the second part, which is the second sub part, which is really loop quantum gravity. And this, by contrast to string theory, was developed mainly by people who started out in general relativity community. And here, the main idea is quite different. It's not unification, but the general idea is really stems from Einstein's outrageous idea when he discovered general relativity, namely that gravity is not a force, but a manifestation of the curved nature of space-time. And therefore, inclusion of gravity in classical theory needed a new syntax, because as soon as you have gravity, you have got curved space-time manifold, and therefore special relativistic description is no longer sufficient. And one needed the new syntax of Riemannian geometry. So everything, Maxwell theory was described in Riemannian geometry, or we've got a curved space-time metric. There's the electromagnetic field, which is a tensor field on this manifold, which is propagating following the null cones and causality given by this curved metric, and so on. The loop quantum gravity viewpoint is that same thing should be true when we go to the quantum theory. Quantum gravity also needs a new syntax, and now from all known physics. And therefore, this new syntax would be like the Riemannian geometry that provided us the new syntax to formulate all of classical physics. And now the new syntax would be a quantum version of the Riemannian geometry. And therefore, this was systematically developed by a very large number of researchers in the 1990s, including some people who are in the audience, like Carlo Rovelli, also Jurek Lewandowski, and so on. and Thomas Tiemann. And the central theme here is that gravity is
Sorry,
encoded.
Abhay, did you change the slide to number 10?
Say it again.
We are at slide 9, which is a summary of string theory, and you have
I
moved
change
on.
it to 10. You don't see the 10 one?
No, no, we don't see 10.
Because I see 10 on mine. You don't see 10?
Anybody else sees 10?
Nope, I
No,
don't
we
see
all
any.
see
No, we all
the
see 9, Abby.
Okay, so I'll stop share and start share again and see
Yeah,
what
let's
happens.
do that. Let's do that.
Thank you for pointing out that because I was halfway through the style and
Yes.
uh, desktop. Do you now
Yes,
see?
yes. Now it's good. It's good.
Okay, yeah. If this happens again, please stop me.
Sure, sure.
Okay, so general relativity is founded on Einstein's outrageous idea that gravity is not a force but a manifestation of curved nature of space and time, and therefore inclusion of gravity needed a new syntax, and that was a Riemannian geometry. And the loop quantum gravity viewpoint is that quantum gravity needs yet a new syntax now for all of known physics, and that would be the quantum Riemannian geometry. And it was systematically developed by a very large number of researchers in 1990s. So this is where I was. So the central theme is gravity is encoded in geometry, as I said, and the emphasis is that there should be no background fields, and therefore it is said to be background independent. And also the emphasis is on using non-perturbative methods. So you just don't start with a background space-time and do perturbation theory on it. Everything is non-perturbative to start with. And the contrast with string theory is really that we don't need higher, there are no higher dimensions. A negative cosmological constant is not needed. Supersymmetry is also not needed. In fact, the theory is much simpler without them. And the focus is just on gravity rather than on unification of all interactions. So it is a bit like what we do for quantum chromodynamics for strong interactions. People had first thought that to have a theory of strong interactions, one would need the grand unified theory, but that is not the case. And so similarly here, the focus is mainly on gravity. But it is not a conventional quantization of a field theory because metric, as we'll see, is emergent in a certain well-defined sense. And the underlying quantum Riemannian geometry, we got geometrical observables, they have discrete eigenvalues like the energy levels of a hydrogen atom, the minimum non-zero eigenvalue. So there is a zero eigenvalue, and then there is a minimum non-zero eigenvalue, and therefore it's called the area gap. And that area gap delta naught numerically turns out to be about 5 Planck length squared. And that plays a key role in the definition of curvature operator. Because as most of you know, the curvature, we can define it in terms of holonomies of connections. Then you take a closed loop, you define the holonomy, divide by the area, and then shrink the loop normally to zero size, and that ratio goes to the local curvature at the point. And here the idea is that, well, since we got a non-zero, minimum non-zero value, we only shrink the loop to this minimum non-zero value, and that tames the curvature, and that, in fact, gives a maximum upper bound to the curvature. And therefore this delta naught, the area gap, turns out to play a key role in the definition of curvature and quantum dynamics and quantum Einstein's equations. But the discreteness of this spectrum of the geometrical observables is sophisticated. It's not just like harmonic oscillator type, but the area levels actually crowd exponentially. So the continuum limit is approached rapidly. Go to the next slide. I hope it works. It works.
11, 11. Yes. Yeah, we see 11.
Yes. Yes.
Okay, 11, right. So this quantum geometry provides the syntax to describe general relativity, how general relativity is modified at the Planck scale. And these modifications naturally lead to the resolution of strong curvature, space-like singularities of general relativity. Away from the Planck regime, the space-time continuum of general relativity emerges on coarse graining, that is to say, probing physics on scales much larger than the Planck scale. then we can ignore the atomic structure of the gravity, of geometry. Since the radius of the proton is 10 to the minus 13 centimeters, about 10 to the 20 times Planck length. So if you were to envision the proton as to be as large as the hydrogen atom, if you were to envision the Planck length to be as large as the hydrogen atom, then proton would go from here to the moon. So it's absolutely huge, astronomical thing. And therefore, we don't have to worry about the discreteness of the hydrogen atom in that case. So similarly here, we don't have to worry about the discreteness of quantum geometry at the Planck length scale when we talk about protons. And we can freely use the continuum approximation even at the highest energy experiments in CERN. So the current status of loop quantum gravity is that progress was made by focusing on symmetric gravity sectors, by cosmology or black holes, where limitations of general relativity are most prominent in terms of Big Bang and black holes. These investigations led to novel insight, and the conceptual issues such as the problem of time and endpoint functions in absence of background spacetime have also been addressed. To address conceptual issues like what happens to Big Bang and black holes, we just need a generalization of the Hamiltonian theory, and I'm going to focus on that. But to talk about the endpoint functions, we need spin forms, which is the path integral approach within loop quantum gravity. That has been developed really very, very much over the last 20 years. And that is what is needed to calculate these endpoint functions. But there still are major gaps in our understanding of full quantum dynamics in absence of symmetries in both the Hamiltonian or the canonical approach and in the path integral approach. And also the connection with effective field theories at low energies is just beginning. But still we have concrete results, as I will illustrate in a minute. The potential constraints on the standard model of particle physics remains largely unexplored. The main ideas and thrusts are summarized in the pedagogical chapters written by leading researchers in loop quantum gravity, and they appeared in a monograph, Loop Quantum Gravity, in a series 100 Years of General Relativity. And there's also an introductory outreach YouTube video, 75 minutes, the story of loop quantum gravity from Big Bang, from big bounce to black holes. And here you will see discussion of both the path integral approach or the spin form approach and the canonical loop quantum gravity. And of course, about quantum geometry itself. So I've done the first two parts. It took some time, but I thought that this is sort of setting the general story. And now I would like to go to fundamentals of loop quantum gravity. But if there are some brief questions on the first two parts before I go into the loop quantum gravity and then theory versus observations, perhaps people can ask them now. Can they just speak, or you have to?
Yeah, speak or raise the hand, use the hand icon, or say something in chat. Yeah, any of that.
Hello.
Yeah.
Sudhakar, go ahead, please.
Yeah. I'm just wondering that can I get Newtonian gravity from the loop quantum gravity?
Yes. So classically, the statement is that general relativity. Classically, we begin with a theory which is completely equivalent to general relativity. And general relativity, you can take the Newtonian gravity limit, right?
General relativity, I know, but I thought that you just started from the quantum Riemannian geometry.
Right. And so this quantum Riemannian geometry.
How do I go from there to Newtonian gravity?
So what one has to do is one can use some what we call effective equations. In other words, what we have in quantum theory, what we have is really a wave function of various geometries. But in some certain good situations, even in cosmology or on black holes, what one can do is, at macroscopic black holes, what one can do is to construct a state which is sharply peaked about some classical solution to Einstein's equation, if you like. And so, for example, one can get something, equations like the Friedmann equations, Einstein's theory. And then, just as we can sort of think of getting Newtonian dust equations from general relativity, we can get the effective equations of general corrections given by the effective equations sort of from loop quantum gravity, as we'll see, become completely negligible, and therefore the effective equations could lead you with the suitable approximations to standard Newtonian gravity. I mean, if effective equations give you the same answer as ordinary general relativity, and we'll see in a few minutes that is the case, then that would give us that would also would take us then in the non-relativistic limit to Newtonian theory.
Okay, thank you.
Okay, let me continue then. So basics of loop quantum gravity. So this is a bit more detailed now, and this is so there is actually I hope you see this slide which says basics of loop quantum gravity.
Yes. Yeah. Yes. Yes.
So there is a dramatic shift now, and namely that now the starting point is a connection as in gauge series rather than metrics as in general relativity and Euclidean quantum gravity. And a contemporary perspective of these new results and these directions with this viewpoint is given in this 2021 paper with Madhavan Varadarajan. So the idea is to reformulate general relativity as a gauge theory with no background metric. The phase space is the same thing, same as in Yang-Mills theory. It's a vector potential, non-abelian vector potential, and the conjugate electric field also carrying an index which is the Lie algebra of the gauge group, which in this case is SU2. But without a background field, so there is no metric there. So it's not like a standard Yang-Mills theory. And then if you don't have any background fields, there are very few gauge covariant expressions you can write down. And the only ones that are at most quadratic in A and at most quadratic in E turn out to be precisely the Einstein's equation in the Hamiltonian form. Now, you would say, well, but you have this Yang-Mills theory and Einstein's equation really refer to the metric and so on. How does this arise? Well, the spatial metric QAB is a derived quantity obtained by declaring that these electric fields, the objects with the internal indices, they really can be thought of as being three vectors which are orthonormal triads, and technically with density weight 1. And therefore, the Riemannian geometry is emergent. So to begin with, I don't know anything about the metric, but I just interpret this as being an orthonormal triad and define a metric in terms of that. So this metric arises from a background independent gauge theory. In the metric picture, the Wilson lines of this connection that we got up here, or holonomies, they parallel transport the left-handed spinors or the chiral spinors of the standard model. And this emphasis on connections, and we don't start with the metric, but connections, metric is emergent in this case, they bring general relativity closer to other basic interactions. Now, there is a confluence of ideas from Rogers, from Penrose's spin nets, and also twistor theory. In fact, I was deeply influenced by the nonlinear gravitonic construction of Rogers when I was a postdoc in Oxford, and these new variables came soon after that. In terms of connection variables came soon after that. And the ideas from Newman on so-called edge spaces or heavenly spaces, and Plabansky's self-level gravity, and Dirac theory of constraint systems in the canonical form, and the Feynman path integral in the spin form, and of course gauge theories themselves. So then the statement now we can say that, well, let's pass to the quantum theory, starting with this classical theory. And then important techniques from gauge theories are the following: that we got these Wilson lines, which are path order integrals of A dot dl, and there are also smeared electric fluxes on a two-dimensional surface. You can take electric field and look at the flux of it. An electric field has an internal index, so you need a test field with also an internal index, the Lie algebra. And these two objects, they serve as a basic phase-space variable, generating a Poisson algebra on the Yang-Mills phase space, if you like, that we started out with. So if I did this, I could just be doing it on Yang-Mills phase space. And in fact, something like this is done in the lattice gauge theory on Yang-Mills in Yang-Mills theory. But this Poisson algebra between them, however, has no background fields. And therefore, these operators can be promoted to quantum algebra, just like the Heisenberg algebra of Q hat and P hat in quantum mechanics. But now the difference from Yang-Mills theory is that in Yang-Mills theory, we've got a space-time geometry in background. So when you look at the representation of this algebra, we're allowed to use that space-time metric. Here we don't have a background metric or any other background field. And there is a powerful uniqueness result that was shown by Lewandowski, Okala, Salman, and Tiemann. Namely, which is background independence implies that this algebra admits a unique representation by operators on a Hilbert space subject to the standard regularity condition. Now, this is vastly different from what happens in ordinary quantum field theory in Minkowski space, where the field algebra admits infinitely many representations, and the free field representation is just the Fock representation is just one of them. And if you wanted to do really rigorous mathematical field theory, then Fock representation cannot be used in presence of interaction. Whereas here you get a new representation, which is quite different from Fock representation, which has certain fundamental discreteness built into it. But infinite dimensional issues are fully controlled. There is a regular normalized Borel measure on the space of generalized connections. This quantum configuration space is the space of generalized connections. And then we've got a Hilbert space of that. We've got wave functions like that. And there are no background fields, such as a metric. And we only have a manifold in the background. And therefore, we've got diffeomorphism covariance. As we will now see, quantum Riemannian geometry emerges from this setup. Namely, diffeomorphism covariance simplifies the analysis significantly. And this rigorous framework was systematically developed by a very large number of researchers, which have been listed here. And in particular, Baez, Gambini, Lewandowski, Marav Okala, and Rovelli, and Smolin. And in this picture, what happens is really that we have got quantum Riemannian geometry really emerges very naturally. The fundamental excitations of geometry are given by Wilson lines, and they are one-dimensional and polymer-like. And continuum arises only on coarse graining. So the fundamental excitations are like this, for example. And these fundamental, if you give me a two-sphere, in this case, you can envisage it as a the horizon of a black hole at an instant of time. Then these excitations, fundamental excitations, intersect. And each time they deposit a quantum of area here. And therefore, the total area is made up of sum of all these quanta. So the fundamental excitations of geometry are given by Wilson lines, and they are one-dimensional polymer-like. And spin networks, they provide us with convenient basis that diagonalizes geometric operators, such as areas and volumes. As I just said, area is really resides at the intersection of any surface with these one-dimensional excitations up here. These are the quanta of area. And the quanta of volume reside at the vertices of this spin network. So this is a spin network. Each of these lines up here, which is line up here, carries a label. And that label is really like an angular momentum label. And that tells us how much area is deposited here. 1 quantum, 2 quantum, million quantum, and so on and so forth. So this label will tell you that. And similarly, all these ingoing lines up here, they are joined together to make them invariant and by an intertwiner. And this intertwiner, together with the information about these labels which are joining up here, they give us the quantum of volume here. So the chunk of volume of space-time is really, so to say, is this node encaptures a chunk of space-time. And label link, as I said, deposits the quantum area on its surface. There are well-defined geometric operators like the area of a surface and a volume of a region, and they are discrete spectra, just like those of the hydrogen atom, the Hamiltonian, L squared, and Lg. And in particular, of interest is the area gap. As I said, it provides us an upper bound for curvature. Now, there are some long-standing questions of quantum gravity, which has been there forever, which are nothing particularly to do with loop quantum gravity or string theory or twistor theory, etc. And one of these ideas, one of these questions is, how do you do physics if there is no space-time metric to anchor it? Second idea, what is time and how do you speak of dynamics or happenings? A third kind of idea, the third question that arises, which is confusing if you don't have a background metric, namely that normally in general relativity, strong curvature, there are curvature singularities, and are the strong curvature singularities naturally resolved by quantum gravity? And what about the ultraviolet divergence of quantum gravity? Are they resolved by quantum gravity? And so the answers from loop quantum gravity are following. How do we do physics if there is no space-time to anchor it? Well, what happens is that matter fields and geometry are both quantum mechanical at birth, but quantum fields propagate on the quantum state of the geometry. And this quantum state provides geometry, provides a probability for various geometries, right? And the analogy is with electrons in a laser beam. Supposing I got a laser beam, I got some electron there. So, of course, to first approximation, you can think that the electron just is passing in a classical field, which is where the coherent state is peaked at. But, of course, there are quantum fluctuations, and the electrons will sense those quantum fluctuations. So, similarly, the statement is that we got a quantum geometry, the quantum matter fields are propagating on that. To zeroth approximation, it will, if the state is like a coherent state, then, of course, to zeroth approximation, it would seem like the quantum field is propagating on a classical space-time. But of course, then if you look at quantum gravity corrections, you will see the fluctuations of the geometry appear that are felt by this quantum field. What is time and how do you speak of dynamics or happenings, if you don't have any space-time background geometry? Well, a matter field can serve as a relational clock with respect to which other fields evolve. For example, in cosmology. In cosmology, the simplest clock is just use a scalar field in cosmology, a zero rest mass scalar field, which is just propagating, satisfying the wave equation in the Friedmann background, for example. And just at the classical level, you can reinterpret this scalar field as a clock with respect to which the volume of the universe, the anisotropy of the universe, and maybe other matter fields that may be in the universe, that they all evolve. And then that can be taken over in quantum theory, and this is a large work by a whole bunch of people in the years starting roughly 2005 to 2015. An example of how do you mean something is happening, right? I mean, we don't have a space-time geometry in the background. What do you mean by happening? And this is provided by spin forms. So here basically is a path integral approach. So you have got some initial state and you got some final state. The initial state is different from the final state, as you can see here. The spin network state here is different from the spin network state here. And that occurred because something happened here. Namely, at this particular vertex, you actually, the space-time vertex, you actually had some bifurcation. Something happened here that created new edges and also created a chunk of volume up here. And so this happening is really new nodes with a chunk of volume that can be created or they can be destroyed in a spin form. Are strong curvature singularities of general relativity naturally resolved by quantum gravity? In all cosmological and black hole models considered so far, space-like strong curvature singularities are attained by loop quantum gravity. Nothing is infinite there. You can evolve the quantum state across what was the classical singularity. In cosmology, it is not just the Big Bang, which is what happens when we got the standard matter. But with exotic matter, you can have these different kinds of strong curvature singularities like big rip and sudden death. For big rip, the scale factor becomes infinite suddenly at a finite time. And with sudden death, the acceleration of the scale factor, so to say, becomes infinite at a finite time, and so on. Even those singularities are naturally resolved by loop quantum gravity, by the corrections that come from the quantum geometry in loop quantum cosmology. Are the ultraviolet divergences of quantum field theory naturally resolved? There are some concrete results on regularity of matter Hamiltonians due to Thiemann, and that is really because the quantum nature of loop quantum gravity just sort of compensates for what was like diverging in the matter Hamiltonians. But we do not know how to systematically relate these effects to the effective theories. And that, of course, is an outstanding and important problem and is still open. Okay, so I'm done here with the fundamentals. And now the last main part, which is really theory versus observations, the very early universe. And then if there's the issues, we'll talk about questions from organizers and the status of black holes in the discussion period, if there is interest. Okay, so I hope you see the next slide, which is theory versus observations and the big bounce. The Big Bang, what happens to Big Bang in loop quantum gravity? Well, what happens is that it is replaced by a big bounce. For concreteness, I'm going to consider inflationary paradigm. But loop quantum gravity people like Param Singh, for example, has worked with so-called like periodic one, and Ed Wilson Ewing has worked with other ones, which are matter-dominated bounces. So there are work in other paradigms as well. But for definiteness, and because a lot of work in cosmology is done with loop in inflationary paradigm, the Kobe, not Kobe, but the Planck results are really interpreted using the inflationary paradigm. And so let me just use that here. Now, I think it is this paradigm has been highly successful, but it is not a fundamental theory like general relativity. Rather, as Jim Peebles says, it serves as a framework on which to hang a theory. And that is my attitude too. That is something like the Bohr atom, which is not the final theory. It's, in fact, many conceptually it's quite wrong, but on the other hand, it turned out to be very, very useful. So we're going to use inflation in the same way. Now, inflation begins much after the Planck regime, where matter density and curvature have decreased to about 10 to the minus 11 Planck scale. So there's considerable work in this loop quantum gravity to extend it to the Planck scale, and there are many, many people who have worked on it. And what happens, as I mentioned, is that the Big Bang is replaced by the Big Bounce. There are no infinities anyway. So you've got a contracting universe up here, and then it goes out to expand out here. The curvature here at the bounce is very, very large, but it's not infinite. It is about 62 times Planck curvature, which is Planck length to the minus 2. Therefore, the background geometry, which is in this loop quantum cosmology, it depends on the scale factor and whatever matter fields you got, that remains well behaved. And the cosmological perturbations that grow into large-scale structure propagate on this quantum geometry. So I know epoch up here, you get some cosmological perturbations early on, and these are here. The quantum nature of geometry is very, very important near the big bounce, and therefore these cosmological perturbations are actually affected, and they go on there. And the evolution has been studied by different groups, leading to a bridge between theory and observations. So singularity is actually resolved. For example, this is Starobinsky potential, which is very heavily used in cosmology because of many of its attractive properties. And here I'm looking at the volume of a box. For example, you have a fiducial box and place it somewhere in the space-time and see how this volume changes versus the scalar field. And as I said, what we're going to do is to use the scalar field as a time in most of this epoch up here. So normally the standard inflation starts somewhere here and the inflaton rolls down. And as the inflaton rolls down, the volume of the universe, as you see here, increases. And the value and the inflaton rolls down, so the value of the inflaton actually decreases up here, as you see. But if you take this evolution back in time, if I had used general relativity, then this inflaton would go into a singularity. So the volume would become zero and there will be singularity. But instead, in loop quantum gravity, there is a bounce and the universe bounces and joins on to another branch up here. So what is behind the singularity resolution? Well, the key modification of Einstein's equations are well captured in quantum-corrected Einstein's equations. This is what I was referring to in the answer to the question about do we get back the familiar classical Newtonian gravity or Einstein or general relativity. And the statement here would be that we were to first get general relativity, and then from general relativity, we know how to go back to Newtonian theory. So do we get back to general relativity? So what happens is that we got Einstein's equation, which are here the Friedmann equations, which are in blue up here. Scale factor, this is the Hubble parameter square, A dot over A whole squared is equal to 8 pi g rho over 3. This is the Friedmann equation. It gets modified by loop quantum gravity corrections. And instead of 1, I get 1 minus rho by rho sup. And this is something that comes out of equation straight. We did not know this is what would happen. It was a surprise when it first came out. And the rho sup here is G rho sup is 1 upon length squared. And so it is given by the area gap to the cube times length, Planck length to the 4. So this is really length 1 upon length squared up here. And this is about 0.41 rho Planck. So what happens is that when the density reaches rho sup, the universe bounces. As I said in this picture, you're going back in time, the density is increasing, and when it becomes equals the rho, the supremum of rho, which is 0.41 rho Planck, the universe bounces into another branch up here. Okay. So going back to the slide, which begins with what is behind the singularity resolution, the second paragraph, the mechanism here is that we do not put any unphysical matter with negative, with energy violating, which violates energy condition, or new boundary conditions, as in Hartle-Hawking scenario. But rather, quantum geometry itself creates, so to say, a brand new repulsive force in the Planck regime, overwhelming the gravitational classical attraction. And this phenomenon has been analyzed in great detail using the Hamiltonian approach, the path integral approach, and a consistent histories approach. Hamiltonian approach was by, sorry, I should not be me, it should be B and Pawlowski and Singh, and then and also the path integral approach was with Campigli and Henderson, and the consistent histories approach was with Craig and Singh. And the matter density and curvature operator has an absolute upper bound on the physical Hilbert space. So really, physical observables do not diverge. And this provides a precise sense in which the singularity is resolved. And as the area gap goes to 0, in the Wheeler-DeWitt theory, there is no area gap. As the area gap goes to 0, rho sup becomes infinite up here. So this term disappears. You get the classical equations, and then the singularity is not resolved. So in the Wheeler-DeWitt theory, singularity is not resolved. But in loop quantum gravity, it is because of the quantum geometry effects. And there is this new meaning of the Big Bang that has come up, namely that this idea, the idea that the singularity is resolved, and therefore there really was not a Big Bang. There was never a kind of a singular beginning of the universe, etc., has become very much mainstream in cosmology, although exactly what was there and what was before that and so on is debated, and people have very, very different ideas about what is happening here. But nonetheless, this is a short, I think less than 10 minutes video up here in which Roger and Stephen Hawking and I think it was Vilenkin and Guth and Veneziano and I were interviewed up here. And you sort of see here that even in the mainstream cosmology, the idea is that the universe really didn't begin with this Big Bang, but rather what in the mainstream cosmologists now say that Big Bang is really a hot phase in the very early universe, which is after the inflation, so to say. People who believe in inflation, they say it's after the inflation, not before the inflation at all. So it is worth seeing this. But I think it's fair to say that this idea that there is no Big Bang, but there's a big bounce came first in loop quantum gravity in detail. Now, what one can ask is a question, this is all fine, but what about observations, right? From fundamental theory to observations. Conceptually, loop quantum gravity bounce is attractive. But how would we ever know that there is a big bounce rather than a Big Bang? Information about the early universe comes from the cosmic microwave background. Won't the effects of pre-inflationary dynamics be completely diluted during inflation to leave a mark in CMB? And this was the standard viewpoint in inflation people doing inflation. They never worried about what happened before the inflation because they said whatever happened doesn't matter. It will all be washed out because of this exponential expansion um, during inflation. And the answer is no, that is not correct. Because if there were actually some excitations or the so-called Bunch-Davies vacuum, which is what inflation uses at the onset of inflation, so if the state of the cosmological perturbation was not described by the Bunch-Davies vacuum, but by some excitations or this Bunch-Davies vacuum, then during inflation, these excitations are not diluted because there is stimulated emission in addition to the spontaneous one. There is also stimulated emission of these excitations, and these excitations are not diluted. Their density actually remains a constant, and therefore one would actually see them also at the end of inflation. And this was pointed out by Aguirre and Parker quite some time ago. And this was a change. The inflationary people were surprised by that, but this is now accepted by the mainstream inflationary people. The curvature at the bounds is finite and has a universal value. So curvature radius is therefore non-zero. In general relativity, the curvature is infinite and the curvature radius the curvature is 1 upon curvature radius squared. So in general relativity, that will be 0, but now it is finite and is about 8 Planck length. So the cosmic microwave background modes of perturbation, which have a wavelength less than the loop quantum cosmology scale, they are actually not affected by by the pre-inflationary dynamics. But those with which wavelength larger than this length scale are affected. This may seem a little counterintuitive at first, at least to me it did, when we first found this, but it's in fact what one would expect. Because, for example, when I'm walking on Earth, I don't feel the curvature of Earth, but when I'm flying, if the wavelength is much larger than compared to the radius, or is comparable to the radius, then I do see the curvature of Earth. So here, the Morse whose wavelength is much smaller than the LQC length scale, they don't see the effect, these quantum fluctuations which have been introduced by the pre-inflationary dynamics, but these ones do, the ones which are long wavelength do. And among the observable modes, it turns out that these modes are the ones which are the longest wavelength. And they carry the imprints of pre-inflationary dynamics. So there is a cosmic tango, as I would like to say, between the very small and the very large. This scale comes from the very small, from the Planck scale dynamics. But this scale then says that imprints will be visible in the longer wavelength modes appear, the longest wavelength observable modes appear. And interestingly, the predictions from standard inflationary model fits very well with observation for most modes, but not for the longest wavelength modes. And for these, there are some anomalies. Now, people don't take them too seriously because the statistical significance of any one anomaly is low. But two or more anomalies taken together imply that if the standard inflationary scenario is correct, then we live in a very exceptional universe. With two anomalies, it means that we live in a universe which is 1 in a million among those which will be just printed out by a computer given the initial data. Therefore, the anomalies and mechanisms to elevate them have drawn significant attention. So, for example, the Planck mission themselves emphasize this point of view. This is from the first 2015 release, and this is from the last 2018 release up here. And here they say the case for anomalous features in CMB has been strengthened. Hence, such anomalies have attracted considerable attention in the community, since they could be the visible traces of fundamental physical processes occurring in the early universe. And in 18, they say if anomalies have primordial origin, then their large-scale nature would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring any models that might explain an anomaly, and even better, multiple anomalies naturally with very few parameters. And in loop quantum cosmology, that's what is done. People have looked at this effect of this longest wavelength modes and shown that, in fact, these longest wavelength modes do lead to departures from standard inflation, and these departments alleviate the anomalies. So it is really the longest wavelength modes which are excited by the pre-inflationary dynamics of loop quantum cosmology. They experience curvature in the pre-inflationary phase, and that is why we have got some excitations over the Bunch-Davies vacuum at the start of the inflationary phase, and these excitations are in the longest wavelength. Therefore, for most of the cosmic microwave background, the predictions of loop quantum cosmology agree with those of standard inflation. But for so-called L, which is the YLM L less than or 30 or equal to 30, the modes which are L less than or equal to 30, so very long wavelength modes, they are the ones on which for which the pre-inflationary dynamics of loop quantum cosmology leave signature in the cosmic microwave background that alleviate the anomalies. And this was kind of done in 2020. And what we found was that in the standard cosmological model, we got 6 parameters, and 5 of them remain essentially unchanged. Less than a fraction of a percent, actually. Between loop quantum cosmology prediction and the standard inflation prediction is the same. But the 6th one, called the optical depth, which measures how long reionization lasted, that increases by about 9.8% in loop quantum cosmology. So it is written down up here in red up here. So the black ones, they don't change much at all, but this one actually changes quite a bit. In the 2018 last release of Planck, all parameters but tau were measured to less than % accuracy, as you can see up here in this, while tau has 13% error bars up here. These error bars up here. The forthcoming mission should measure it to 1% accuracy, and then one would be able to distinguish between them, because the difference between these is about 9.8%. There have been missions since 2018, and the general tendency is actually increasing the value of tau, so it is in this direction, but the error bars are still very large. The best was about 7% that I checked last time. And so getting to 1% would be very high. And the last thing that I wanted to just point it out here in terms of technical thing is the following. That I've been talking about this area gap. And now what we can do is, this area gap came into loop quantum gravity by considerations of black hole entropy, which I did not discuss, but we can discuss it in the discussion period. So its value was fixed by looking at the black hole entropy. That area gap we know there is a area gap, but its value is not fixed in loop quantum gravity. It has to be, we need some external input. It's a bit like the theta parameter in QCD. We need experimental input to actually determine it. And loop quantum gravity then assumes, based on black hole entropy, one assumes this up here. But what we can do is, in cosmological calculations, what we can do is to let the area gap be not this value, but let it float. Let it be varying. And we can then ask for the probability. How do cosmological observations actually constrain it? So we get a posterior probability distribution function. And in fact, this area gap is within 1 sigma. The area gap of loop quantum cosmology is within 1 sigma, 68% confidence level. And increase in area gap by a factor of 10 is observationally ruled out at 95% confidence level, and decreased by a factor of 10 at 68% confidence level. So this is something that we had not at all anticipated, because this value came by some, that black hole and completely mathematical physics and number theory function, counting of states and such thing. And then the statement is that we let it vary, and cosmology also is agreeable with it. Okay, so let me just finish with the summary, and then we can have a discussion if there are questions. So the problem of unifying general relativity with quantum physics has been open for a century, because all the well-established physics to date is anchored in a fixed space-time geometry. We need a new conceptual and mathematical syntax to work with a probability distribution of space-time geometries. We have apparently quite different approaches, because different communities have different tests and styles. built on past successes. This diversity is not only healthy, but in my view, is essential because we don't have too many experimental observational checks on quantum gravity. So I think this diversity is very, very important. What is lacking is robust dialogues between various communities, but this has begun to change, but not enough, I think, just slightly. Although we do not have a satisfactory and definitive theory, there has been notable progress on many fronts. Developments in quantum field theory in curved space-times, and that is what led to Hawking effect in the first place, and also to the cosmological perturbation theory and agreement with the analysis of CMB, understanding the fate of classical singularities of general relativity on quantum gravity, creation of a syntax for calculating the endpoint functions without a background geometry, use of relational time in quantum cosmology, for example, hints on how quantum gravity could constrain particle physics, and this is more from asymptotic safety paradigm, a very rich set of tools from string theory, which are applicable to QCD, which are applicable to fluid dynamics, and so on. In my view, the progress has been slow but steady. Personally, I'm most excited by the fact that quantum gravity has left the lofty perch of abstract mathematics and making contact with observations, as we saw in the very last part, where we talk about cosmology. Our current ideas may be wrong, as they often were when quantum mechanics and particle physics were developed in the early days, but observations can guide us and constrain us. So this, to me, I'm most excited about the fact that there can be actually suggestions like this here, that there are some parameters which could be better measured that will provide us guidance about how to proceed, what is correct in the model building, and what needs more attention. Okay, the very last slide, a reminder from Feynman. I think it is sort of important to keep this in mind, in my view. And I think a lot of people who work in quantum gravity, for good reasons, they're mathematical physicists because the problem is so hard. But I think some attention to observations and nature is really needed here. So, for example, in the literature, we got such quotes. It says, "It would have been a cruel God to have laid down such a pretty scheme," and these are supposed to be the H spaces that Newman has developed, or heaven, "and not mean anything, something deep." Similarly, about string theory, "I just think too many nice things happen in string theory for it all to be wrong. Humans do not understand it very well. But I just don't believe there is some big cosmic conspiracy that created this incredible thing that has nothing to do with the real world." I think the check is given by Feynman. He says, it does not matter how beautiful your theory is. It doesn't matter how smart you are or what your name is. If it doesn't agree with experiment, then it is wrong. And I think it is good to keep this in mind. Again, I gave some examples here from history, but maybe I shouldn't go into that because I've gone over time. So let me stop here, and then we can have discussion if there is interest or other questions.
Thank you very much, Abhay, for a beautiful lecture. I'm sure there'll be questions. There are already a few in the chat. And for other questions, kindly use the raise hand feature to ask your question, and then we can proceed. Yeah, Roger, good to see you. Good evening. Go ahead, Roger.
Hello. Can you hear me?
Yes, yes.
Oh, good. No, fantastic talk as usual. Thank you very much. I thought that was
Thank you, Roger.
However, there's an issue which you didn't touch upon, which I think I'd like to bring up and get your opinion on. The idea is that you look at how quantum theory would affect gravity or space-time and things like that, which of course is a very important issue. But there's the converse issue, which is that quantum mechanics has a real problem. And the real problem is the collapse of the wave function. And I have a view that this is a gravitational effect, and that we have the opposite, the gravitization of quantum mechanics, as opposed to the quantization of gravity, which I regard as equally important, but in a sense more immediate. Because the thing is, you actually have quantum mechanics all the time, and the wave function collapses all the time, and we have to understand that. And so to understand that problem is more immediate in a way than these issues that you are so wonderfully discussed in this talk. I just wondered what your view on this is.
Yeah, as you know, Roger, I mean, a long time ago when we were writing the one of the first books that you were writing about, I had done this calculation. I took this view very seriously that the gravity may be involved in this wave function collapse, and I was doing this calculation of how many gravitons you need before the wave function collapses and so on. So I take this very seriously. And also, I do have a paper some time ago written actually in the volume in honor of Engelbert Schucking, which showed that it is with Troy Schilling. It says it is about precisely geometrizing quantum mechanics. In fact, that quantum mechanics is too linear, and perhaps there is a manifold structure and so on. So we formulated it in the language of manifolds and basically just the symplectic structures, and then there's extra structure which is a metric and so on and so forth in quantum mechanics. But we can make this metric curved and what happens in that case, etc. So I think that is really a very interesting and very deep problem up here. But as time has evolved, I personally feel that it's not clear to me that it is necessarily gravity that is going to do it. I mean, the usual thing I used to think of was, well, if it's not gravity, what is it? I think that it may be something much more basic, namely, maybe the wave function doesn't collapse at all. It is just an approximate description. It's a very convenient description, but it's an approximate description. And that, in fact, what is happening is that the wave function is extremely become sharply peaked. Now, why does it become sharply peaked? I don't know. And in other words, when interaction, I mean, what we have is really a closed system. If you take the measuring apparatus as well as the system, then the pointer points in one way, so there is an interaction between them, but we'll have to take into account. We should really look at the total system, look at its evolution. And so the total evolution may well be perfectly unitary or nonlinear version of unitarity that I was pursuing. But a subsystem could still show some effects which are approximately, to very good approximation, reproduced by wave function collapse. None of these ideas have been formalized, etc. But that is my general direction of thinking these days, that somehow it is not so much going to be dictated by gravity, but our whole framework of quantum mechanics is something is missing there. I mean, that what we have is really an approximate description. I mean, it's not it's a bit like we have the Bohr atom for measurement problem. Bohr said that, well, we got these orbits that are quantized and that's it. But on the other hand, everything is classical. So I think something else is happening, and it could be geometrization of quantum mechanics, as you said, doing non-linear version of quantum mechanics that actually leads you to this conclusion. Is almost flat, but not exactly flat. In other words, Hilbert space is a good approximation, but not a very good approximation, etc. None of these are coherent things, but these are just directions in which I've been sort of thinking in general.
Well, thank you for your comments.
Yeah, Roger, something more?
Well, I had another question, which is a different one, which has to do with the cosmology. I wonder whether you have any thoughts about these recent observations made by Alexia Lopez of these huge rings of galaxies, which seem to be there. She found two of them. Well, one was a big arc, and then the big ring. These are several times the diameter of the full moon, I should say, so they're enormous, whereas extremely distant. And she sees there was the big arc, which she tells me is actually a ring. And I think she's found a third one. So we see at least three of these ring structures, which are so huge that they couldn't have come. I mean, the origin of them would seem to have to have been within before the turn off of inflation. I don't actually believe in inflation. I don't think it makes any sense, but that's a separate question. I just wondered whether you had any comments about the
So
new
I mean, I'm
observation.
not an astronomer. I cannot really judge what she has said. So I would like to see a little more. I'm waiting to hear what other people say about it, so as to weigh it in some ways. Because somebody's making a claim, but then people might say, people who know, professional astronomers might say, oh, but it could be explained this way, that way, or they may say that's really puzzle. But since I'm not a professional astronomer, I don't know how seriously I should take it at this stage. So at this stage, I'm on hold. I'm watching it, but don't have any really opinion about it. Yeah.
Well, I suppose I'm slightly biased to be in favor of this feature because it can be understood in terms of the CCC picture, where rather than the bounce that you talk about, we have the remote future of a previous eon becomes the Big Bang of our eon, because at the crossover from one to the other, you have a situation where you lose the scale, and you lose the scale because in both cases, mass effectively becomes irrelevant. I won't go into that because that's a different theme.
But I'm also sympathetic because for example, Ed Wilson Ewing, one of my former students, he has done some careful work, looked at CCC, and has said that, well, can the predictions of these rings that you had before, can they come out of the bounce picture? And they have paper showing it can come out, and they also have paper showing what one needs, if what ingredients one needs, which are not tied down to any particular theory, but just general thing about perturbations in early universe, how they will reproduce this thing. So there's a whole bunch of things. So I'm also interested for the same reason, namely that this could also be compatible with the bounce. And so that's why I'm watching it and see if it is.
Yes, well, the question is whether the bounce would annihilate information. I mean, I guess that's
right, but that's the analysis that they did, right? They showed that in fact, I shouldn't go because it's a long story. It's I can send you again. I sent you a reference to this paper some time ago, but I'll send it again, and so you can take a look at it. And so
okay.
It's Wilson Ewing, and they looked at the CCC and the bounds and compared and so what happened.
Thank you. Abhay, I want to follow up on Roger's first point. And my take is that current formulation of quantum theory is approximate and not ready to be used to quantize gravity. And the reason for saying that, as you say, quantum mechanics needs external classical space-time background. In my picture, such a classical space-time background coexists with classical macroscopic bodies such as stars and galaxies. If the universe is not dominated by classical bodies, I would not have a classical space-time. And since classical bodies are a limiting case of quantum theory depends on its own limit in this sense and is hence approximate. I would look for a...
But I don't agree with many things that you already said. So
Okay, let's stop here. Let's discuss this. Yes.
Yeah, so because I think the statement is that you say that somehow we need massive bodies, but I mean, observations are completely compatible with Einstein's general theory of relativity. And your point was that there are no massive bodies. Now massive bodies are very dilute. They're going away. It's going to be dominated by cosmological constant. And yet all observations...
No, not lambda. Unless the universe is dominated by classical bodies, I cannot have a classical space-time manifold.
That's not true. I mean,
No,
I can have a classical... That's your
concept.
philosophical prejudice, and that is perfectly you're entitled to have it. But it's incompatible with general relativity, and so you're saying general relativity is wrong because general relativity
Not at all. General relativity is right.
But general relativity does have a lot of solutions which are just pure radiation. I mean,
okay. I see. Yes, but I
pure
don't
gravitational radiation. There
I
are no
don't want.
matter bodies at all, and these
I don't
these
want.
solutions
I
are...
think that's philosophical. I don't want a physical space-time in which there are no matter. I
Yeah,
don't
so you
see
can
it
have
as.
philosophy, but I mean, we are
Yeah.
just taking general relativity as a starting point, and I agree that
Okay.
once you have this philosophical principle
Yeah.
that in fact, space-time comes to existence only with these bodies and so on, then all bets are off. But I don't have that philosophical
Okay,
principle. I
great,
just
great.
take,
Good, yeah,
yeah.
yeah. Good
But
that
that
we
is where the
sorted
difference
out.
is.
Good
Yeah,
that we sorted out. I'll just complete the story. So
sure.
then what we went after is to look for a formulation of quantum theory in which we actually seek to remove classical space-time, even Minkowski space-time. So what we did is, when, for example, replace each space-time point by something like a quaternion or octonion, then the symmetry groups of the octonion algebra admit as a subgroup SU2R cross U1 along with SU2L cross U1 electromagnetism. So we see that the analog of the electroweak theory is the SU2R cross U1. U1 is a new interaction. The SU2R is very much like your use of SU2 in your LQG approach. So that what encouraged us is just as SU2L, the weak interaction by itself is not renormalizable, but electroweak is. Similarly, SU2R cross U1 is a renormalizable generalized gravity in which U1 is a, you could call it, let's say, dark electromagnetism. So we find that quite interesting. So have you thought about parallels between weak force and gravity?
Yeah, but I think that there are similarities and there are differences. And differences is, in my view, that gravity is what determines space-time geometry. So the statement is that if you can, I mean, we have got very rich, um, we got very rich information that has come from gravitational waves and black holes. If you can have some idea about how that is, and it's very detailed from LIGO observations over the last 10 years. So if you have any idea about how to get it without saying,
ডিসকাশন চলছে এখন, ঠিক আছে, বন্ধ করে দিয়ে আসছি।
Sorry, Sudhakar, please mute, please. Sudhakar, please mute. Please mute. Abhay, go on, please.
yeah. So the statement would be that that if, I mean, there are many gravitational phenomena. I mean, you might just want to look at electroweak interactions or particle physics interactions, for which something like this might be, very interesting and very. But if you want to bring in gravity, I don't see how to do the most important thing that we're seeing, right? I mean, like the early universe and the black holes and gravitational waves from them. If
Can
any
I
of
know
these
that?
can come without space-time, that would be great.
No,
That would be very
space-time
good.
must emerge. Space-time must emerge in the classical limit. And we are trying to think of general relativity as being equivalent to our SU2R Yang-Mills theory. There are difficulties, but so your point is good that gravity is a geometry of space-time. The weak force is not. So it turns out perhaps there is a second 4D space-time as a part of our universe, which has three time and one space. And the weak interaction is the geometry of that space-time, but can be also interpreted as an internal symmetry.
Yeah, so that would be more like issue that will come up when you discuss unification or something like that. Namely, how I mean, this is a bit like non-commutative geometry. I mean, what
Yes,
your
yes,
program, and
yes.
and and so it is. It doesn't tell us very much about quantum gravity. I mean, it is.
Yeah,
I
yeah.
mean, the
Quantum
actual
gravity.
model has only two copies of Minkowski spaces and hardly. I mean,
No, no. SU2R gauge theory is what I would call a precursor to quantum gravity. I don't quantize the geometry. I quantize the connection in your sense, but in the classical limit, the metric and geometry emerge.
yeah, I think if one can show that, that would be fantastically interesting. That classical
Okay.
limit will get general relativity, but quantum mechanically, there's only this connection, and this is what is important. I think that will be very, very interesting if one can show that.
Okay, great. Thank you. Thank you. Thank you.
I think there are two
Carlo.
people who have been
Yeah.
asking,
Yeah,
Jitu
Carlo,
and
go on,
Carlo.
please. Jitu. Okay, Jitu first. Jitu, you go first. Jitu, can you unmute yourself, please? In the meanwhile,
Um,
Carlo.
uh,
Okay, yeah, go ahead, Jitu.
First of all, thanks for the lecture, Professor Ashtekar. I like to ask a question to Professor Ashtekar. Professor Ashtekar, I'm just a 19-year-old kid actually, so I don't actually know much on theoretical physics. But you have actually mentioned that the UV incompleteness problem of loop quantum gravity, like. String theories historically have been critical of this the loop quantum gravity, that it cannot have a UV complete thing, right? There is actually a recent development from the particle physicists like Sohar Komargodski, that they can actually complete the UV complete quantum field theories without having the density matrix equal to 1, or without violating the Coleman Mandela theorem. So don't it just imply that there would be some easiest way to map to the UV complete problems from the loop quantum gravity, in which we don't even consider S matrix for framework, right? Even string theory does have these kind of bootstrap things, right?
Yeah. So that there are several questions that you're asking. So the first is that in so far the in loop quantum gravity, the emphasis is on gravitational issues, particularly about the singularities, about black holes and Big Bang, and there is, and this unconceptual issues like how do we handle time in absence of a space-time background, and also these endpoint functions which come or this actually there are endpoint distributions which are coming from. What does it mean in a diffeomorphism covariant theory? These are very hard questions, and these have been looked at using spin forms. Spin forms also provide you some S metrics, if you like, but that S metrics is a finite S metrics. We don't know how to go from infinity to infinity or from scri minus to scri plus, etc. But there's work that is going on right now. But you also said something about loop quantum gravity not being UV complete. I mean, I don't agree with that. I mean, we're not established that it is. We're not calculated the S matrix elements for sure. We're not calculated that with the interactions. But on the other hand, I mean, it is UV complete in the sense that we're actually shown that singularities are resolved. String theory never has not shown that any physically interesting singularity is resolved at all. So with the results that you're quoting just now, if they can actually tell me how a black hole or Big Bang singularities are resolved, how to deal with non-extremal black holes, just ordinary Schwarzschild black hole, then, and particularly what happens near the singularity in these models, what the space-time looks like, etc., then I would take it much more seriously as a candidate for UV complete theory. But otherwise, I don't see that as UV completed. So neither do I agree that string theory or these approaches people have written right now, which may be quantum field theory kind of approach, that they are UV complete because they will have to answer these questions which we don't know how to answer. I mean, they don't know how to answer, but loop quantum gravity does. And it's certainly true that loop quantum gravity has to do work in order to do the S metrics properly.
Professor Ashtekar, also the string.
Jitu, could you kindly wait, please? We'll go around and come
okay,
back.
fine, I can wait.
Carlo, go ahead, please.
Thank you, Tanada. Hi, bye. Thank you for this very wide-angle presentation of quantum gravity. I found it very, very interesting. It was meant for people who are outside the field, but was super interesting for me also. I mean, being much more closer. Of course, I agree with.
It was not meant for
Yeah,
you.
it was not surprising that I agree with so much about it. I have a comment about one detail. Is actually a detail related to Roger's first question, which is the specific comment is how much gravity changes quantum mechanics. And I wonder if you agree with that, with the following. Is it that I don't want to enter into the sort of measurement problem, interpretation of quantum mechanics. I mean, that's definitely not the point to entering in a debate in which there are many opinions and super interesting debates around. But specifically, I want to make a comment about what we, including me and you and people around us, often say. we formulate, we say, well, we keep the core of general relativity, the main equations and blah, blah, of course, going to quantum theory, and we keep quantum mechanics as it is. So quantum mechanics is not affected by gravity, which in a sense is true in the way we do it. But for many people, there is an ambiguity in language, seems to me, because for many people, quantum mechanics is a synonymous of the Schrödinger equation. And Roger is one of these persons. I took very seriously many of his criticism, pointing out to the fact that there is an incompatibility to the Schrödinger equation, understood as an exact equation of nature, and gravity. Okay. Now, the way we go around it is not to keep the Schrödinger equation as an exact equation of nature as it is, but to interpret quantum mechanics a bit more widely, so to say, in which time is internal, in which we somehow we have the Wheeler-DeWitt equation or whatever we want to put it. So in a sense, we are modifying quantum mechanics in this weak sense. We are modifying quantum mechanics to make it compatible, to make it general covariant, because instead of being evolution in a single external parameter, is sort of an internal evolution. You explained in your presentation, for instance, you see how things evolve with respect to a field inside. So it seems to me that in this debate between you and Roger, which actually continues since you were a kid, if I get it right, okay, you've been debating, you and Roger, that for a lifetime. There is a sense in which Roger says, look, strict Schrödinger equation does not fit with Einstein phenomenology. And if I may, we're wrong in saying, no, Roger, you're wrong, it does. Yes, it doesn't fit. In fact, it fits with a slightly wider interpretation of what quantum mechanics is, in which you don't have a t parameter. So the correct criticism that Roger pointed out are right, but we do quantum mechanics a bit more wider with a sort of covariant formulation of quantum mechanics, a Wheeler-DeWitt formulation of quantum mechanics. Would you agree with this characterization?
Yes, I agree completely with what you said, but that does not really ask. I mean, that does not really say, well, then I pop measurement. I mean, you do the way you want.
No. It's not to do.
It does not answer that question. Then that is the question that is left open.
It's a side remark. It doesn't
Roger would say that. Then tell us what happens.
Yes, but it distinguishes the measurement problem from a certain confusion, seems to me.
No, I agree. That I think
coming to the fact that, look, generative is incompatible with the Schrödinger equation. Yes, it is.
Yeah, I think I agree completely. What we're doing is not a standard quantization of a field theory kind of thing that we're done. I mentioned it, but also in your sense, in conceptual sense. But maybe Roger wants to add something, I think.
Perhaps I could make a comment about, you see, the reason that gravity is to play a key role with regard to the collapse of the wave function comes from the equivalence principle. You see, the equivalence principle holds for gravity and not for anything else. Now, if you look for the Schrödinger equation written in an accelerating frame, and if you like, you compare the Schrödinger equation where you think of the gravity as a force, and you put the term in the Hamiltonian as you would with any other force, and the alternative point of view where you regard it as an accelerating frame, the local field of gravity can be eliminated by free fall. But this is not quite so straightforward, because you look at the actual form of the Schrödinger equation and you see that there is a term involving the exponential of the cube of the time. And let me just make the point that gravity has a special role in relation to quantum mechanics, which no other force has. So when people say, well, maybe we've got to modify quantum mechanics, but maybe it's not gravity, it's something else, I say there's a good case for it to be gravity. And this comes way back to the foundations, where you look at the foundations of general relativity, which is to get rid of the gravitational field as a force.
Yes.
And the principal equivalence says it's just.
I got it. If I may, if I'm allowed to, Roger, I think one thing I'm saying is that it's not that we have not listening to that. I have listened to that very carefully, and I think the argument is correct. The point is that there is another alternative, not only the one you say, which is to do quantum mechanics without a Schrödinger equation, which is what we have been doing.
But can I say something, Carlo?
Yeah.
Even the standard quantum mechanics with the Schrödinger equation is pre-assuming classical space-time background to be present. And my point is that that is an approximation already. Abhay has a different viewpoint on that. I would like to see, even at low energies, quantum mechanics rewritten without any reference to classical spacetime, and I personally think that is the way forward. In non-gravitational theories, it's okay because gauge theories can live with a external classical background, but the attempt to quantize gravity, in my view, faces this paradox that writing down the rules of quantum theory pre-assumes gravity to be classical. Then I'm saying now I will apply these very rules to gravity itself, and it makes me uneasy.
I don't agree that gravity is that that we're using the rules of quantum mechanics require that there be a what you said something that there should be a space time. No, what a
That,
given
that
space time.
the rules of the rules of the rules of quantum mechanics, in my view and understanding, require gravity to be classical.
No, so I think that is where I disagree. I mean, it may be semantics. I mean that you can modify quantum mechanics in the standard quantum mechanics in a way which again maybe semantic. One might want to say that this is a profound modification. This is no longer quantum mechanics, and I'm fine if one wants to take that philosophical point of view. But this is what we did about quantum fields on a quantum space time. This is the paper that Jurek Lewandowski and Kaminsky and I wrote, which has to do with the precisely addressing this question. I mean, normally all these questions, these problems arise, but we can actually talk about quantum fields in quantum space times.
I think I agree with you.
This is not addressing the measurement issue. I'm not
I
talking about
agree.
collapse of the wave again. But in writing the framework, you can talk about quantum fields
When you now that you put it this way, Abhay, it looks reasonable to me. Maybe then what we are missing is what is the choice of the correct quantum space-time. So I'm claiming that we found octonions as a quantum space-time to be very promising. Maybe we are agreeing that using different languages. Yeah.
Yeah, philosophically, yes. But on the other hand, I mean, as I said, I mean, it's good that we have got diverse approaches because I think the problem is hard. So I don't want to say that, one approach is string theories used to have that point of view very strongly that anybody who is not
Well,
doing string theory is wasting their time. And I think that viewpoint is
I
not right.
think in my view, the fundamental problem with string theory is that it set out to explain the world of particle physics that we see, and it does not succeed in doing that. And that is the end of the story as far as I'm concerned. In fact,
Okay, I
I
shouldn't
want
have brought in string theory. I shouldn't have brought in string theory.
yeah. No,
But I just want to take the point of view that
Sorry to interrupt. I just want to mention one thing that me and my group and our collaborators, we are back to E8 cross E8, but with a very different outlook than that of string theorists. Gravity is very naturally embedded in this E8 cross E8 as a SU2R cross U1. So in my understanding, E8 cross E8 was good, but string theorists didn't use it properly. That's my outlook.
yeah, I'm not sufficient expert in particle physics to sort of have any expert opinion. I just follow it at a distance, everything. So yes, sir.
Okay, thank you. So we could go on. I'm sorry to make Andrew Hamilton wait. Andrew has a few questions in the chat. First is
Okay.
GR is bosonic, but your spin networks have half integers and integers. Do fermions and the exclusion principle emerge as part of LQG?
No, so the fermions are put in just like I mean, it's a matter field that you put in, which is you can put in Maxwell fields, you can put Dirac fields, you can put Young-Mills fields. So it's one of those fields that one is put in. So I mean, at this stage, loop quantum gravity does not have. It's not like supergravity, in which it says matter has to be this. I mean, it's more like general relativity, which says that it does not make any demands on matter. So I could put in fermions, as we do put in all the time, fermions. So it's not.
Can I
Yeah.
follow
Yeah,
up
please.
on that?
Yeah.
On that question. Yeah, it does seem to me that fermion spinners play an absolutely fundamental role in the physics that we actually see in nature. And so it seems to me, I would be inclined to think that a fundamental theory like LQG should have them built in from the get-go. And again, I'm going to push you. You put spin half on your spin networks. If LQG doesn't actually already contain those things, what legitimizes labeling them
Oh, so
spin
I'm so
half?
sorry. Yeah, so I should not call it spin. It's just a representation. It's called spin, not in the physical sense. It is called spin in the sense of representation of label of representations of SU2.
I understand that.
Yeah, so that they're not in the spin network itself. It is not. It is really a polymer excitation of gravitational field. It is not, does not refer to fermions or anything like that. So it is really a representation of SU2.
Well, spinners are a representation, the spin half representation.
Yeah, I know, but you can have mathematical representation. I mean, I can just say that it's a holonomy. It's an element of SU2. Okay.
I understand.
And then what I'm doing is I'm just saying that, well, but mathematically to treat this thing, it's better, it's easier for me to go to representations and use the standard theorems to expand out any function on the group as being, using the representation. So that's what I'm doing. But I'm not sticking with spin 1/2. I mean, all the spins are appearing there. Right.
Okay.
In the usual
maybe I should. Yeah. Maybe I should move on to the.
No, but your first question was very good, because I mean it was relevant for LQG, because in fact when I was a postdoc with Roger, that was one of the things that impressed me, that the self-dual connections of gravitational field actually exactly are the ones which are tailored to the standard model, right? I mean that they could be emphasized is something that came because of this, precisely the fact that in the standard model the fermions are they're left-handed, and therefore we should use this representation. So that is what it came from.
Maybe I should move on to my second question, which does LQG generically yield a bounce at a singularity, or does that require a special kind of symmetry, like spherical symmetry? And notice there's a similar question later in the chat about what happens to the entropy during collapse.
Okay, so let's look at the first question here. So the statement is that, well, I mean, the detailed calculations have been done in systems like the Friedman universe, but there are also the Bianchi type universes and spherically symmetric black holes. There is no complete general result which says that in LQG there would be because of dynamics of LQG would be such that no singularities would ever be formed. We don't have such a result. But what all
of the examples that you've just mentioned have a high degree of symmetry, including the Bianchi, which are homogeneous. So I find it very extraordinary when one actually has collapse to a singularity. It's not a stable thing from the classical point of general relativity.
What do you mean it's not a stable thing?
Well, it's chaotic, like the BKL oscillations.
No. Okay, I think that's a long discussion we should go into. Okay. Okay. So, I mean, I think that BKL behavior also has been analyzed in detail using loop quantum gravity techniques. So you can, in fact, some BKL blogger was saying that if one thing survives from loop quantum gravity, it would be this analysis of BKL using loop quantum gravity techniques. So we looked at that. I mean, but But I think that, and this was a work with David Sloan and I think Ed Wilson, Ewing, and Henderson. I think these people. So, no, but your point is well taken. I mean, we don't have a general theorem. I was hoping that just like the Hawking-Penrose theorem, we would have no singularity theorem instead of singularity theorems, right? I mean, somehow under generic condition and under collapse, the singularity is don't form. I mean, I'm still thinking that this is perfectly possible, but we are not there. We're not there. The detailed calculations have been done only for symmetric models, and I emphasize that in my talk also, that the detailed calculations are only for symmetric models. Okay.
So Andrew, could we come around? I see that you have more questions, but I would request people who have put their questions in the chat to kindly please say it out so that everybody gets a chance. If you have left a question in the chat, please use the raise hand feature and ask your question so that the discussion flows easily. Anthony, please go ahead.
Hi. Yeah. Thanks very much indeed for the talk.
Thank you.
So I just wanted to ask about the Big Bang, well, the Big Bounce, in relation to the topology of the universe, and whether there's any preference for closed universes, particularly from the point of view that they're finite. So you've got a finite surface that you're working from. Does that have any implications?
It does have, but on the other hand, the bounce is there for both the flat, open, and closed. Closed have been looked at very much, and in particular, as you say, because it's finite, you can ask more questions there, right? I mean, we can ask for example, is it? I mean, one of the intuitive things that people often thought was that, in fact, in a finite universe, the universe will collapse to a Planck size and then expand. But this is not at all the case. I mean, in simple models, at the bounds, the universe can be absolutely huge in the compact one, because if it's a flat one or open one, it's always infinite. So there's no. But here it can be absolutely huge. I mean, it can be. I mean, it all depends on which initial conditions you give. So let me tell you how it is done. It is done by giving some initial conditions, and if you like, it's done by giving the initial condition now and evolving backward in time and seeing what happens. So now I can give you various closed models, right? So I can give closed models which for example, they start with a Big Bang, they expand out to the maximum slice, and then they again collapse up here. So we can parameterize them by their maximum slice, just maximum size. Now, this was done 20 years ago, so I forget exact numbers, but roughly speaking, I think, we say that, well, supposing the maximum size is quite small, I mean, I know 100 megaparsecs or something like that, or maybe maximum size is that. Then what happens, right? When does the bounce occur? If I evolve it back in time, then when does the bounce occur? And the bounce occurs when the universe is of the size of a mountain, because that is when the curvature becomes Planckian. So the bounce occurs when the curvature becomes Planckian and doesn't have much to do with the size of the universe at the bounce. The size of the universe at the bounce is determined by the parameters of that particular solution that you are considering at late times.
But presumably then, in the closed case, it will carry on oscillating.
Yes.
Yes.
So, but yes, absolutely, and it will keep on oscillating. Exactly right. And then we also calculate how much it changes in time, and from one epoch to another, how much radius of the bounce. It's supposing it bounces the first time around at 100 megaparsec. Then in the oscillating the second time, how much does it do? And these changes are negligible, and we looked at it, and you would need like 10 to the 50 bounces for this departures from general relativity at the macroscopic level to be found.
Right. And one link question. So in previous talks in this series, in fact, we've heard about CPT symmetric universes from Neil Turok and Nathan Boyle, where it has a lot of implications if you insist on CPT symmetry as you go through the Big Bang or Big Bounce. I mean, is that something you've looked at, or does it come out
No, we don't
automatically?
have no. So the statement is that it's not true that in this bounds is symmetric in the sense of, the past branch is just time reversal of the future branch. I mean, it depends on the details of the system. Sometimes it is, but sometimes it's not. It depends on the initial conditions. So it's not we don't have we don't have that CPT symmetry.
Okay. Right. Thank you.
Thank you.
Thank you. Thank you, Abhay. Thank you, Anthony. Bernd, please go ahead.
Thank you for the very nice and illustrative talk. I would add another question on fermions. You said that you can put them on your, let's say, quantized space-time. How is this done, and can you do this without changing the geometry? So can you still work with the Riemannian geometry, or do you have to add additional geometric degrees of freedom to incorporate fermions?
Okay, so you're talking at the classical level or quantum level? I mean,
quantum level.
Yeah. So quantum level, I think this is I showed the spin networks, and there were the spin labels there, and they were meant to be just excitation of geometry. That label was a SU2. It was a quantum. It is carrying that much quantum of area. That is what it was. But on the other hand, if you have fermions, then the fermions also live at the nodes. Just at the nodes of that graph up here. So it lives at the nodes. And then the statement is that in that case, if that says electrons, I mean, just to make it simple rather than something with the internal degrees of freedom, then I will be actually electromagnetically propagating them. So therefore, this the holonomy will be not only gravitational holonomy, but also have a Maxwell component in it. This holonomy would be right. So there will be two different components to this. So it's a bit like lattice gauge theory, if you like, except that the lattice is itself giving meaning to space-time, rather than there's a space-time and I introduce a fixed lattice to it, etc., etc. So the way that fermions are treated is, I mean, mathematically it may look like doing something on a floating lattice, by floating, in the sense that it's not a rigid lattice because that lattice at the same time gives meaning to space-time and also to fermions which are propagating in that space-time.
But you can still work only with curvature, or do you have to add torsion?
Good question. You can do it either way. So you can just work with, you can do it either way. So it's simpler if you add torsion, as you say. I mean, in other words, if you work in the Einstein-Cartan point of view, then sorry, not Einstein-Cartan, but just Cartan point of view, then there will be torsion, but you don't have to have torsion.
You don't have to.
Yeah, you don't have to have torsion. I mean, in Lagrangian, there's a term which you can absorb in one way or the other. It's up to you to. It depends on the interpretation. There's a term built out of the fermion currents. Yeah. I mean, this is actually something that is discussed in some detail in the paper, which was written long time ago, about I think 89 or something like that, which was written with me and my then students Romano and Tate. In which
then I will look at this.
It's a physical review letters, a physical review paper, but detailed paper.
A physical review. Okay, then I will. Thank you. Then we'll look this up. And just a brief follow-up question: do you have a kind of decoherence to get from your quantized space-time to classical space-time?
That is a possibility, but that's not how it is done currently. I mean, currently the statement is that it is just like a coherent state, right? I mean, in Maxwell theory, if you have a coherent state of photons in Maxwell theory, that approximates the classical field very well. And with tiny fluctuations. So the people have done the same thing here, namely they consider the nonlinear analogs of those coherent states, particularly in the spin-form models. And
and if I got it correctly, you do not quantize time. It's relational or emergent, right?
It's exactly. It's emergent, right? Exactly. The curvature is quantized, and time is
Thank you.
relational.
Thank you very much.
You're very welcome.
Thank you.
I guess we should wind up soon.
I think it's time. So could I ask a closing question? So maybe if you could kindly stop sharing the slides so that we can see everybody on the screen.
I'm not seeing this.
No, I think if you close the slides, all the pictures, all the small pictures will.
No, I'm not sharing slides. It says, I don't know what's happening. I think you were just saying, okay, this AI companion, I can close that.
Somewhere there should be a stop slide share. And if it's not there, it's okay. There's no problem.
Yeah, okay, stop share. Maybe. Yeah, maybe.
Yeah, this is good. This is good because we can see all of us together on the screen. Yeah. So
I don't see anything. My view has not changed, but maybe your view has changed. Good.
Okay, I'm sorry.
That's fine. I see Roger.
Suppose we say that loop quantum gravity is a work in progress. What would you like to see? What would you like to see as results and outcomes which would convince you that yes, this is the correct quantum theory of gravity?
Okay, that slightly two sub questions here. I mean, I think that if in fact, for example, in near future, the optical depth is, I mean, I said that recent measurements actually are saying that optical depth is larger than what the standard inflationary model have been using, have been concluding, then and if it turns out to be what LQG says, it should be within 1 sigma and exclude the standard picture, then I know there's an observational evidence that we should be. So that would give us a lot of confidence that we are on the right track, so to say.
Mm-hmm.
And then there is a conceptual question. So that's several conceptual questions that I would like to see very much. One is, I think it came up several times, that what compared to, say, particle physics and string theory and so on and so forth, we don't know much about S-matrix theory. There, the emphasis is often on S-matrix theory, and here we don't know much about S-matrix theory. And I think there's the work has begun, particularly with the Perimeter Institute, Bianca Dietrich and her group and so on, in which when we're trying to make contact from LQG, so spin forms particularly, because they are better suited for S-matrix kind of questions. So making contact with effective field theory, but I would like that contact to be much more strengthened. Right? And so I would like to see that, in fact, that we do get correct the effective field theory. There's a bridge which is sort of we start at the Planckian level. Effective theory starts at low level, and that is actually a bridge. To me, that I think is a conceptually important thing. And for that, one of the things I'm pushing very much is that for this, there's a lot of work on scattering theory using Scri plus and Scri minus, so celestial holography they call it, and there's a lot of very interesting results there. So I think the idea would be to me, I mean, this is very feasible in near future, to really use loop quantum gravity Hilbert spaces at Scri plus and Scri minus and see what the S matrix looks like in that. So that I think would be, in terms of conceptual mathematical question, would be very important. The second thing is that I didn't get to that at all, neither did I get to the questions that you had asked in the discussion period. But there's a whole work on black hole evaporation, and at the very end, there's a phase. There's a phase of the evaporation one in loop quantum gravity. The singularity is resolved, but yet, and so the information, there's no problem about information coming out, and but we don't have a full theory, because there is a small regime in which our approximation methods fail. Currently, our approximation methods are very good. If curvature is low, or curvature can be Planckian, but it's changing adiabatically. It's not changing dramatically. But the very end of black hole evaporation, both these approximations fail. Curvature is large and changing extremely rapidly. And so there, I would need some new techniques, new approximation methods, and I would love to develop them. So these two things, if one can develop it so that we really have a complete picture of the black hole evaporation, and on the other hand, we have a good contact with effective field theory and S-matrix theory, that I think would be, to me, very satisfactory. And then there is a question about contact with observations. What I like about loop quantum cosmology is that that is one place where one could make contact with observations.
Thank you. Michael, any final remarks?
I like to ask a question, like it was a continuation.
Abhay, are you taking more questions?
I can take one more question, but
okay. Last.
Thanks, Boss Ashtekar. Actually, Professor Ashtekar, I think you actually misunderstood what I have said. Actually, there is actually some recent developments in UV complete quantum field theory that you can actually have symmetry breaking even at arbitrarily very high energy. So I think.
Okay, tell me what happens to the black hole evaporation in that theory. If it's UV complete, tell me what happens to
tell
me what happens to the singularity at the
black hole.
But then,
okay.
But the UV complete theory
yes,
should tell me what happens to the
that.
singularity, right?
Yes, I do acknowledge it.
Yeah,
but,
so when the words are used in a certain way, and by UV complete, one means as a quantum field theory, that quantum field theory does not have infinities that are does not have ultraviolet infinities, or they don't have to be renormalized. It gives you the full answers in the ultraviolet, but it is restricted to that quantum field theory. That doesn't mean that you have got quantum gravity theory.
Yes, correct. It does not mean actually. What I have said is actually, isn't this a complementary result that the loop quantum gravity theorists can actually use? That was the question I was
my talk was restricted to quantum gravity. My talk was
agreed.
Okay, thank you, Jitu, thank you, Abhay.
I think I have to come in here now and say.
Okay. I just wanted to say one thing, that it's really wonderful to see Roger, because I've missed seeing him in Oxford during this conference this summer, because Christine was not well. So I'm really happy to see Roger.
Yes. Good to see you too.
And we are happy to see both of you on the same screen.
Well, yes, indeed. We're very happy to see both of you, and indeed everybody else who's taken part. And thank you, Abhay, for covering a simply enormous amount of ground, very, very clearly. At the same time, going into considerable detail in the Q&A. I've certainly learned a very great deal. Thank you very much for all your patience, and keep up the good work.
Thank you.
From my side also, Abhay, thanks so much for accepting our invitation. It was great to listen to you.
Oh, and can I just say very quickly your very last parting remark about where you thought both the possible experimental developments would be, the place where you'd look for those, and the conceptual developments, particularly to do with connections with S-matrix theory and effective field theories. Those were extremely illuminating, and I'd love to correspond further, perhaps, about those things.
Sure.
Thank you. Thank you again very much, Abhay. It's been a wonderful talk. Thank you for talking.
Thank you, and thank you, TP, but also everybody. It's been a pleasure interacting with everyone. Thank you.
Yes, thanks to everybody for coming. And
thank you all. So I am now closing the discussion. Goodbye. See you next time.
Bye-bye.
Yeah. Bye-bye.